Time to look at some inelastic collisions. We already mentioned these in the last video, that this is where you lose some kinetic energy in a collision, and particularly we're going to look at what are called perfectly or completely inelastic collisions. In that case, the two objects stick together. So they stick, and our equation for conservation of momentum, everybody's favorite, m1v1 plus m2v2 equals m1v1 prime plus m2v2 prime. Well, if they stick together, then v1 prime equals v2 prime, and so we could just call it v prime because there is only one final velocity. And then we can factor out the masses, so you'll end up with m1 plus m2 quantity times some final velocity. And these types of problems are pretty simple, but we'll do a quick example anyway. You got a couple of train cars, one initially at rest, the other moving, collide together, so we're just going to plug into that equation. Since v2, not prime, is 0, our equation just becomes m1v1 equals m1 plus m2 outside of v prime, and then we can just plug in our numbers here. We've got a 10,000 kilogram car times 24 meters per second. It doubles, so this is going to be 20,000 times v prime, and as you might expect, the velocity gets cut in half, so 12 meters per second. Because we doubled the mass, it doesn't always get cut in half. So there's a nice easy problem. Now the League of Sadistic Physics teachers decided that we want to make harder inelastic collision problems. So what we do is we give you less information and then you have to use other stuff. So here's an example of that. This device here is called a ballistic pendulum, and these are actually used in real life. It's not some fictitious figment of physicists' imagination. And they're used for finding the velocities of bullets. And what you do is you fire a bullet into this block. The block rises up a certain height, and you can measure that height, and from that you can go back and calculate the initial velocity of the bullet. Now if we try to just use conservation of momentum, because this is a completely elastic collision, we've got a problem, and the problem is these wires here. So we collide and momentum is conserved, and that's all fine, but as this thing swings up, there's another force being exerted on this block, so we're transferring some of the momentum through the wires to the building or whatever, and we're not going to be able to measure that amount. So we might think we could use conservation of energy. And we know we don't know what it is, but we know we have kinetic energy here and then just gravitational here, so you might try to set those two equal to each other. The problem is, if you're going to collide and stick, you are going to create some thermal energy. You have to. Even if we go back to this simple example here, if you calculate the kinetic energy ahead of time and the kinetic energy afterwards, even though there was no friction considered at all here, these just stuck magically, I guess, you will lose some kinetic energy. You have to create heat in this process, even in a frictionless environment. When things stick together, they create some thermal energy. So in this collision here, there's some thermal energy created, and if all we know is this final gravitational energy and there was some thermal energy created, we won't be able to figure out what our initial kinetic energy was, and so we won't be able to find that velocity. So what we have to do is we have to combine the two approaches. So we have to use conservation of momentum for part of the motion, and then we need to use conservation of energy for the other part of the motion. And there will be different types of problems, like cars smashing together and sliding off, where you will use this same approach. So if we call before the bullet strikes situation number 1, right after the bullet collides but before the block has moved significantly, we call that situation 2. And when the block is at its highest point here, if we call that situation 3, then we can look at how these two things are going to be related. So the initial momentum is going to be in situation 1, so I'm going to call it P1. Now I said when these wires are pulling on it, it transfers momentum that we're not going to be able to keep track of, but before that happens, here at situation 2, that hasn't happened yet, so we can still apply conservation of momentum to situation 2 to find the velocity right after the collision before it swings up. or at least an expression with that velocity in it. Then for energy, the problem with our energy is this thermal energy created, and we didn't know how much thermal energy there was. But if we ignore the thermal energy and just say, well, how much kinetic energy at position 2 is remaining, and that kinetic energy all becomes gravitational energy, Ug at position 3, then we're good on the energy and we're good on the momentum. So this is going to be our approach. Now we can start getting some equations here. In situation 1, the big block is not moving, so we've got mass of the bullet. I'll use little m's for that and big M's for the mass of the block, times its velocity, which we don't know yet. I'll call it v1. And then it's a perfectly elastic or inelastic collision. Was I saying elastic earlier? Sorry. Anyway, inelastic. So we can say big M plus little m, and I'm going to call this v2 just because it applies to situation 2. Now we've got the masses, but we don't have either of those velocities, so we're not done yet. If we come over here, put a line here so we don't get confused, we're going to have the kinetic energy at position 2, which is going to be 1/2 times the combined mass, because the bullet is embedded in the block, so we can just treat that as one object, times v2, the same velocity that we're talking about over there, squared, and all of that equals the combined mass times g times h. And don't really need any subscripts there because there's only one h. Alright, now we can start plugging in numbers, and then we can work our way back to this guy, which is what we were interested in finding. So we've got a 50-gram block and a 5-kilogram 50-gram bullet, 5-kilogram block. So these are all going to be 5.05. And we got a factor of 1/2. We don't know this v2. Here we've got 5.05. G is 9.8, and we are given h is 12 centimeters, so we're going to make that 0.12 meters. Okay, so we can use this equation over here, and we can solve for v2. Turns out that this is equal to 1.5336. Don't do intermediate rounding. Make sure and leave all these digits in your calculator. Now we can plug this guy back in over here. So mass of bullet is 0.05 times v1 is what we're looking for. This is the combined mass, the 5.05 again. And now we can plug in this number for v2, 1.5336. And we can solve for v1, the initial velocity of the bullet, which works out to be 154.9 meters per second. Hooray for making problems hard because it's fun. Okay.